Dear students of physical geography, in the very first lecture on the nature of geography, you have learned how geography is divided between physical geography and human geography. In fact, today we are going to the details of one of the aspects of the physical geography, that is the interior of the earth. This section contains 5 units. Number 1 deals with the introduction to the structure of the earth, composition and characteristics of the earth's crust or lithosphere, the composition and characteristics of the earth's mantle, the composition and characteristics of the earth's core, and lastly we will be knowing something about the importance of the knowledge of the earth's interior. Now let me come to the first subunit, that is introduction to the structure of the earth in general. Planet Earth has evolved to present conditions over the past 4,600 million years. Now it has conducive gaseous layer, namely Earth's atmosphere, water hemisphere, or it is known as the hydrosphere, and the solid earth, which is commonly known as lithosphere. In fact, we are all going today into the details of this lithosphere in the form of the interior of the earth. Let us come to some of the details of the solid earth in this lesson, which consists of another broad 3 layers below the earth's surface. They are earth's crust or lithosphere, earth's mantle, and earth's core, which is further subdivided into outer core and inner core. Now if you look at figure number 1, which contains 3 photographs, namely the position of the earth in the solar system. The other one, when you look at our planet earth from some other, say, planet like moon, the Mars, or satellite like moon, or the other one about the structure of the earth itself. As the temperature increases from the earth's surface towards interior, earth's interior, all these layers with their characteristics and dynamism is understood indirectly. Geologists, particularly seismologists, have studied the movement of the earthquake waves in different layers, which move differently, and have given physical geographer empirical knowledge of the earth structure. In fact, we have a small figure where you can understand how earthquake waves from the point of earthquake origin, they do not move in the mantle straight, because mantle is partly solid, partly liquid. That is why. And in the earth core also it is the same thing. In fact, they are refracted. Okay. Coming to the details of the earth structure, the knowledge of the earth's interior, from these 2 figures, it is evident that our planet Earth has its solid layer, that is the uppermost layer, that is earth crust. Often it is referred as lithosphere. In fact, this uppermost layer has 2 sections which are classified as Sial, top lighter layer, and Sima, the denser layer of the earth crust. Below these 2 rocky layers, as we gradually see, viscous matter layer, namely earth's mantle. It has molten rock in the form of magma, often in big chambers. Below the earth crust and then mantle, we see earth's core, which is further subdivided into an outer core and an inner core, which is believed to be the solid one. The structure of the earth. Let us understand some more details in common about the structure of the earth. From the top of the earth's surface to the center, the earth has a distance of 6,370 kilometers. Temperature and pressure increase with the depth, where the rise of temperature is on an average of something of 1 degree Celsius for every 32 meters of descent. Due to the solidification of the earth since its formation of about something like 4.6 billion years, now it has solid earth crust, below which partly liquid mantle and a solid inner core. As it has been already mentioned earlier, that there are known as Earth's upper crust, mantle and core. There are speculations that the combination of immense rise in both temperature and pressure might have resulted a gaseous inner core, but most of the Earth scientists are of the opinion that under such extreme conditions, Earth's core might be solid sphere. Hence, with reference to the internal structure of the Earth, according to Ulrich and Morgan, that the Earth as a whole is a solid ball, down below under stable conditions behave like a viscous liquid, either through relief of pressure or excess of heat, and thus gives rise to the phenomena of volcanicity. Now let us come to the general composition of the Earth, which can be understood from the following tables. First one gives you how the chemical composition of the Earth crust. Chemical elements like oxygen account for 47%, silicon accounts for 29.50%, aluminum accounts for 8.05%, iron accounts for 4.65%, calcium accounts for 2.96%, nitrogen accounts for 2.50%, potassium accounts for 2.50%, and magnesium accounts for 1.87%. All these chemical composition of the Earth crust is given by percentage, by weight. Then there is another small diagram which shows you how the temperature increases with the depth. In fact, up to the boundary of the mantle, see the temperature continuously rises. There is slight decline, and again further it increases. In fact, the core of the Earth, see the centermost point, which is around 6,370 kilometers, has a temperature around 6,000 or somewhere between 5,000 and 6,000 Celsius. Okay. There is another small table here which also gives how the pressure increases as the depth increases. So it is given in the form of equivalent to atmospheric pressure terms. So around 40 kilometers depth, it is around 10 atm. Around 100 kilometers, it is 31 atm. Around 400 kilometers, it is around 140 atm. And then around 1000 kilometers depth, it is equal to something like 350 atms, and 2900 kilometers, it will be something like 1370, and around 5000 kilometers, it will be around something like 3120 atms, and in the center of the Earth, it is something like 3610 atms. It is all raised to 10 raised to 3 atms. As the depth increases, the temperature and pressure also rise towards the interior of the Earth. It can be seen from the following diagrams as just now I explained. Now let me come to some more details of composition and characteristics of the Earth's crust, or the topmost layer of the Earth. Outermost and the thinnest of the zones of the Earth is the Earth crust, which is often referred to lithosphere. Indirect studies have shown that this has an extent of something like 8 to 40 kilometers or little more from the surface downwards. According to some geologists like Jeffrey, the extent of the Earth crust is still more. It is formed of igneous types of crystalline rocks. Often they are overlaid by sedimentary and metamorphic rocks. Now it must be understood that igneous rocks account for more, and sedimentary and metamorphic rocks have formed little later. Now you see the combination of all this on the Earth crust. But base of all these have still heavier basaltic layer which forms bottom layer of the Earth crust. The crust exhibits properties of brittleness when subjected to mountain building forces and has several macro cracks or fault. The theory of plate tectonics goes into the continental blocks floating on Earth's own mantle along fault zones, and we will learn about these movement of plates in the form of plate tectonics under the theory of plate tectonics little later. Because of the crust where it contacts metal is sharply defined, here earthquake waves change their velocity abruptly. In fact, if you look into the figure number 3 or the figure which shows the details of the earth crust itself, and where you have seen, see the crust has the continental sial, and below that you have a darker layer, denser layer called sima, below which you have a moho, a boundary actually between the earth crust and the mantle. In fact, its details are very clearly given in the another figure 3C. Sial and sima boundary. This line of separation which forms the boundary between the crust and mantle is called moho. A simplification of it is known as Mohorovic, the name of the seismologist who discovered it. From the study of the earthquake waves, it is concluded that the crust consists of two layers, namely a lower layer which is continuous layer of basalt rock also known as sema, and an upper layer granitic rock which termed as sial, which we saw just now in the figure. It further constitutes the continents with a mixture of lighter rocks and a variety of sedimentary and metamorphic rocks, where geology goes into the details of their formation, their chemical composition, etc., etc. However, the granitic layer is either non-existent or it is very thin over the ocean basins. You have to see once again figure 3b very clearly. You can see how the ocean basins do not have sial at all. In fact, they have more of sima. Those parts of the crust forming continents are much thicker than the crust under the ocean basins. It may be compared to vast icebergs floating on the sea with only a small part visible above the water, but with a great bulk deeply submerged. The glassy rock of the Earth's mantle has yielded by slow flowage, much like a viscous fluid. This has permitted the lighter, rigid continental plates of the earth crust to come to rest in the manner of doing the iceberg. In fact, figure number 3C shows how the continents portions also have a deeper roots, and where the continents are very thin, where they have they are very close to kind of sima. Now let us come to the second zone of the Earth's interior, namely the composition and characteristics of the Earth's mantle. Between the topmost lithosphere, that is the crust, and the inner core lies this zone of Earth's mantle. We have to go back to figure number 1, where you can clearly see that how on the thinnermost outer layer, like a line, and between the core, vast zone constitutes this mantle. Okay. It is estimated to be around 2,895 kilometers thick and composed of viscous mineral matter in a solid state. It lies between Mohorovic discontinuity upper side and Gutenberg-Weichart discontinuity towards the core. Judging the formation of the behavior of the earthquake waves, the mantle is probably composed of largely the mineral olivine. It constitutes magnesium and iron silicates, which comprises a basic rock variety called dunite. It is in a glassy state exhibits qualities of a great rigidity and high density in response to sudden stress of the earthquake waves which pass through it. On the other hand, the mantled rock can also adjust by slow flowage to unequal forces that act over great periods of time. Its flowage states can be compared to coal tar, which is hard and shatters easily if struck, but which will slowly flow downhill left untouched for a long time. Earth's mantle is further subdivided into upper mantle and the lower mantle. The upper mantle extends to a depth of 400 kilometers and dissimilarities in seismic velocity profile. S type of earthquake waves do not pass through Earth's mantle and get refracted at the zone of interface. Refer back to a figure 1C, where you can see how different layers of the earth react to earthquake waves. There is also a transitional zone in the mantle between these two zones, which extends towards for about 400 to 1000 kilometers. It is characterized by rapid increase of seismic velocity with increased depth. The lower mantle extends between 1000 to 2900 kilometers, shows a rather gradual seismic velocity increase with depth. The mantle has an overall peridotite ultramafic in composition. Mantle has a massive convection currents of magma which have energized by the heart of the earth's by the decay of radioactive isotopes. In fact, we will know more about under-volcanic activity about this. Earth scientists also have suggested that Earth's mantle of viscous rock material has magma chambers rather closer to upper crust, just below Mohoro boundary, as the upper crust has fissures and other kind of rocks which allow these magma. On movements of plates, magma, the hot molten rock, flows upwards through these fissures and vents onto the Earth's surface. In some cases, when pressure is insufficient, molten rock solidifies in the earth crust itself, giving rise to plutonic landforms. In fact, we will learn more about plutonic landforms like batholiths, laccoliths, dike sills under volcanoes. When magma flows onto the Earth's surface, it is known as lava. We will know more about these aspects under volcanoes. Now, let us come to the third innermost zone and its characteristics, that is the composition and characteristics of the Earth's core. In the last 200 years, mining activities and some scientific studies have provided information about the Earth's composition and its physical properties. However, about the Earth's interior, only indirect observations like the patterns of movement of earthquake waves have given knowledge. A closer study of figure number 3 shows the structure of the earth, which we have already studied, and once again, if you want, you can look back for the details in general and its core in particular. In its 6,370 kilometers of equatorial radius, which is also the straight line distance to its core of the Earth's core accounts for 3,475 kilometers, in which solid inner core accounts for 1,255 kilometers and supposed to be the liquid outer core accounts for 2,220 kilometers. Because of the abrupt change in the behavior of the earthquake waves upon reaching the outer core, it has been calculated that the outer core has the properties of a liquid in contrast to a solid mass which surrounds the mantle. However, the innermost part of the Earth's core with its 1255 kilometers radius may be solid or crystalline. When the average specific gravity of the Earth is 5.5 grams per cubic centimeter, where the surface rocks being lighter have 3 or less than 3. As the specific gravity increases towards the interior of the Earth, as the table already indicated, where it may vary from about 10 to 15 grams per centimeter cube. Further, it is also believed that Earth's core is made up of iron and small proportion of nickel. Hence, the Earth's interior, the core, is often also known as Ni, where Ni stands for nickel and Fe stands for iron. In fact, through the study of the meteors, which are also part of our solar system, have given some information about the constitution of the Earth's interior. Meteors representing the fragments of our solar system, and our planet Earth being a member of this solar system has this kind of composition of the interior. Further, it is also believed that the temperatures in the Earth's crust may be between 2200 centigrade to 2750 centigrades. The core's pressure are as high as 3 to 4 million times the pressures of the atmosphere at sea level. As we have already know at different depths, there is no need to go into the details of that again. Now, friends, let us come to the last aspects of this today's lesson, that is the importance of the knowledge of Earth's interior. Planet Earth is the habitat of man. It has biosphere, which rests on the physical world, which in turn is composed of Earth's atmosphere, its hydrosphere, its lithosphere. In fact, we went to the details of this lithosphere in the form of the various sublayers of the interior of the Earth. In fact, planet Earth has, apart from these different layers, has dynamism. In fact, that dynamism refers to the plate tectonics, through which in the plate boundaries often magma comes to the surface, and also associated earthquakes. In fact, in all these zones, sometimes there will be landslides, land movements. Also in the mountain areas, sometimes avalanches in the form of calamities. All these require the knowledge of the behavior of the Earth's interior. In fact, as we just learned that as we go down from the surface of the Earth downwards, the temperature increases, also the pressure also increases by leaps and bounds. In fact, all these surface movements in the form of plate tectonics have a close link with the interiors of the Earth and its behavior. In fact, the knowledge about all this is very important also for the modern man to utilize or tap the geothermal energy. In fact, all the conventional energy like coal, petroleum, natural gas are going to get over soon. Hydroelectricity is becoming really insufficient. In that direction, either we have to tap solar energy, or on the surface of the Earth we have to go down or to utilize this geothermal energy. In fact, geothermal energy and its utilization needs the scientific and clear understanding of the interior of the Earth. All these aspects also are associated with other phenomena of the Earth, like Earth's magnetism and its measurement, which also varies in different parts of the Earth, and also other aspects related to the dynamism of the Earth. Now, in this particular last section, we have learned about the Earth's interior. In order to understand the Earth's interior, often we have to study the Earth's surface in detail. In that direction, from past 50 years or so or less, Geoinformation System, which is popularly known as GIS, and also Global Positioning System, which recently has been highly used in understanding both the surface of the Earth and also to some extent the uppermost crust of the Earth. In fact, before the application of these GIS and GPS, there is a need for some more detailed understanding of the interior of the Earth, or scientific understanding of the interior of the Earth. Dear students, in this episode, we learned about the interior of the Earth, where we learned about the upper crust, which constitutes the lighter continental layer called Sial. Below that, the Earth crust has how the denser layer called Sima. Both of them, how they are overlaid on a bigger layer called mantle, which is also further subdivided into upper mantle and lower mantle. Between the crust and the mantle, we have a boundary called Mohorovic boundary, and further below mantle, when you go towards the interior of the Earth, how interior of the Earth is known as the Earth's core, which is also further subdivided into outer core and inner core, and where the boundary between the mantle and the core is also known as the Gutenberg boundary, and how still there is still there are some speculations about the exact nature of the interior of the Earth. Sometimes they refer it as a solid, or sometimes it's also referred as sometimes as a gaseous, but however the opinion is more towards Earth's interior is solid, and it's also known as Nephi. Nickel and iron are the major constituents of the Earth interior. Anyway, the Earth as the interior also has a one phenomena called the radioactive decay, and in turn increases the temperature, and also further this decay creates a phenomena called geothermal energy, and that geothermal energy is going to help all of us in days to come in the form of geothermal energy and electricity. Thank you very much.